So let's see why Dijkstra's algorithm really works. Now, it will only work on graphs that have non-negative edge weights. But because this is a greedy method, we need to show that it has the greedy choice property. So we claim that a vertex u, at the moment that it's pulled into the cloud, the distance label that we set for u is exactly equal to the actual distance from a starting vertex v, which is the root of that shortest path tree, from the starting vertex to u. So this is what we set, and this is the actual distance from v to u. And we claim that these things are the same thing. So whenever we add a vertex u to the cloud, we've correctly set its distance label. So in order to prove that this is correct, let's assume that it's not correct, that we're wrong about this, and we'll obtain a logical contradiction, meaning that our assumption that this is wrong is wrong. So let's assume that these are not equal. So that means this distance label, what we set, could be either larger or smaller. Well, it can't be smaller because how we accumulate this distance label is a sum of edge weights along some path. So if we set this incorrectly, then that means we don't have the shortest path. Instead, we found some path, but it was a longer path. So that means that what we set for this distance label is larger than the actual distance from starting vertex to u. So how is this possible? Well, let's see. Here is vertex u. And if there are many vertices like this that have their distance label as incorrect, we're going to pick among all of them just the first one that is placed into the cloud where its distance label is wrong. So we can assume that every other vertex that we've added to the cloud so far, its distance label is correct. Okay, so here's our starting vertex v, and here's that vertex u, which we had only just added to the cloud. So let's draw it this way. So u is the last vertex that we added to the cloud, but this is the first one that was added to the cloud where its distance label was wrong. So how is this possible? Well, if a shortest path from v to u, if this entire path is contained within this cloud to where all of the vertices along it are in the cloud, then we would have correctly set this distance label because the vertex before it, this is in the cloud, was in the cloud before it as well, and this entire thing is a shortest path. And since u was the first one whose distance label was wrong, then if this entire path was in the cloud, then the vertex before it, its distance label would be correct. And then when we update u's distance label, when we relax this edge, we would have correctly updated u's distance label. So if we wrongly set u's distance label, then that means this didn't happen. Instead of having this entire shortest path inside the cloud, then the only way we could have done this incorrectly is if there was a shortest path to u which went outside the cloud. So let's say here is that cloud, and we've only just now added vertex u. And here's a shortest path, which maybe it goes out of the cloud multiple times, but we know at least goes out of the cloud once. So we have a shortest path with multiple vertices and edges along this, and eventually it leads to u. Now let's take along this path the first vertex which goes outside the cloud. Let's call it z. And whichever vertex comes before z along the shortest path from v to u, we'll call y. Now we're going to argue about the distance label between u and z because both u and z are outside the cloud, or were. U was the first vertex we had only just added to the cloud. So why did we add u over z? Because z is still outside this cloud. U we just added. Well, our greedy choice was we always pick the vertex which has the smallest distance label, which means that u's distance label is less than or equal to z's distance label. And z's distance label we know is correctly set because this is the first vertex outside of the cloud along the shortest v to u path. And since any subpath of a shortest path is also a shortest path, then this path from v to z is also shortest. And we correctly set y's distance label because it's inside the cloud, which means when we relax this edge, we correctly set z's distance label. So z's distance label right now is exactly equal to its the length of a shortest path from vertex v to vertex z. Now here's the part where we really need to use that we have non-negative edge weights. So we can say that whatever this value is, the distance from v to z, this is no more than if we were to take that exact same value from v to z and then add something which is non-negative. So by adding the distance from z to u, because we have non-negative edge weights, then we know this will be greater than or equal to 0, which means we can claim that the distance from v to z is no more than the distance from v to z plus this non-negative value. And this sum is exactly equal to the distance from v to u, because we have here the distance from v to z plus the distance from z to u. Since z was on a shortest u to v path, then adding up these distances, we get exactly the distance from v to u, the length of that shortest path. But now we get a contradiction, because we had started off by assuming that we wrongly set u's distance label, that it was too large, and now we just found that u's distance label is less than or equal to its actual distance, which means this is exactly equal to. So this is the contradiction we wanted to obtain, showing that it's not possible that the distance label for u is not equal to its actual distance from v, and our claim is correct. So anytime we pull a vertex into the cloud using Dijkstra's algorithm, its distance label is correctly set. But we really needed to assume, in order to finish this proof, that the edge weights are non-negative. And the proof requires that the input graph has non-negative edge weights, but in fact Dijkstra's does not work if negative edge weights are allowed. If a graph has negative edge weights, then that edge could alter the distance to vertices already in the cloud, violating the greedy property. For example, here we have a graph with a negative edge weight here. Dijkstra's algorithm would have set c's distance label to be 5 going through this path, but in fact there's an even shorter path which is going through this negative edge weight. So we needed a different way to find a shortest path between vertices if negative edge weights are allowed, and they might appear. You'll see how to handle negative edge weights in the next video.